Hello, this video is going to show how to calculate circuit consumption in milliampere hours and then show how to calculate the expected battery life having determined that power consumption. But first, some basic information just to reinforce the points about this particular calculation. So on the left there are various types of battery. I'm going to concentrate throughout the video on the 18650 battery, which is typically 3.8 volts and 2600 milliampere hour. But batteries come in all shapes and sizes: car batteries, dry batteries, rechargeable, lithium, polymer, all sorts of chemistries. But what's common to all is that their capacity is quoted in milliampere hour, or ampere hour. If it's a big battery, a car battery is typically 40 ampere hour. Smaller batteries are typically 2600 milliampere hour. On the left here is I'm just showing capacity of batteries is not always intuitive, but two 2600 milliampere hour batteries in series is a battery with a total capacity of 2600 milliampere hour. Put two in parallel and that voltage there will be 2 times 3.8, 7.6 volts. Put the batteries in parallel and you double the capacity, the voltage remains the same, so that'll be 3.8 volts terminal voltage with a capacity of twice the single battery. And then if you put batteries in series parallel, you can get twice the voltage with the 5200 milliampere hour in this example. So that's, in very quick terms, how battery capacity works out. So again, using a 3.8 volt 2600 milliampere hour battery, you can drive a circuit for 1 hour at 2.6 amps or 2600 milliamps. You can half the current, double the time, so 1.3 amps for 2 hours, or 0.1 amp for 26 hours, or 260 hours at 10 milliamps. Batteries are also quoted in their C rating, which is a capacity rating. The C rating of this battery here is 2600 milliampere hour. So 1C is 2600, 2C would be 5200, and 5C would be 13,000 milliampere hour, or 13 ampere hour. Charging capacities are also often quoted in C ratings. So if a battery is a 1C charge rating, it can be charged at 2.6 amps continuously, or if it was rated for charge purposes at 5C, it would be 13 amp charge rate. In general, the larger the battery milliampere hour rating, the more storage capacity it has, and also the greater the C rating, the higher the discharge or charge currents can be. So a 5C battery can discharge current at 13 amps in my example, whereas a 1C battery for discharge could only supply 2.6 amps. Your circuit power consumption or current in time, using a DVM is by far the simplest, but a DVM on the current range in series with the circuit set to either the milliamp range or the ampere hour range. You will find that a lot of meters, their internal impedance is actually quite high on the milliampere hour range, and that can affect your circuit under test. So for example, it could be a 10 ohm resistor inside the meter, and that seriously creates a malfunction in the circuit under test. So sometimes you may have to go to the higher current range and read the current as 0.01 amps or 10 milliamps. Ideally use an oscilloscope with a series resistor and the signal and ground across the resistor, and if you set it to 10 millivolts per division, the current is 10 milliamps per division, and obviously you can turn up sensitivity or turn down the sensitivity. So if you had it set to 1 volt per division, it would be 1 amp per division. That's quite a versatile method of measuring current, and you get to visualize what's going on. So calculating the circuit consumption in milliampere hours is really all about finding the average value. So I've got two examples here. One example, the top one, the amber one, is a continuous demand of current. It could be continuously demanding 1 amp, and the average value is 1 ampere hour. Or it could be a pulse of current and then a very low quiescent demand of current, and the task is still the same. You have to find that area of the current consumption, find that average. But just to note that the reference point is an hour. It can either be, you can either measure 1 amp for 1 hour or 1 amp for 3,600 seconds. That's how many seconds there are in an hour. And for most smaller circuits, using seconds is probably the best thing to do. So it's all about finding the average current consumption to determine milliampere hour. Okay, here's an example. As ever, an ESP8266 processor which has been set up to send data to a server, and typically it takes a very small amount of current and then peaks for 5 seconds, consuming 74 milliamps every second. Then it goes back to sleep and consumes 0.5 milliamps for 3,595 seconds. 5 plus 3,595 equals 3,600. So that's its current demand, which if I'd put a meter in series, I could measure the fact that it demanded 74 milliamps for 5 seconds and then drop down to half a milliamp, or I could see that waveform on an oscilloscope and determine the same current consumption. In terms of finding area, the area of the first pulse in my example is 74 milliamps for 5 seconds, and then it's half a milliamp for 3,595 seconds. So the total area is 74 times 5 plus 3,595 times 0.5 milliamps. So that's the total current demand over 1 hour. But we need the answer in milliampere hours, so we divide the current by our time reference, which is 3,600 seconds, and you get the result 0.602 milliampere hours. Or in a different way of saying that, the circuit demands 0.602 milliamps every hour, continuously every hour. So it's about finding the average. You find the average by finding the area of every activity within the time reference, that hour between the 2 pointers there, and we're using seconds as our unit of measure. So add up all the samples, that's adding up all the samples and dividing by the sample size, which is 3,600. 0.602 milliampere hour in my example. So the process summary is determine how much time the circuit spends on demanding current and measure the current, and then determine how much time the circuit spends off or in standby and determine the off time and the off current. Sum the total current demand during an hour, so that was 5 seconds at 74 milliamps, and then 3,595 seconds at 0.5 milliamps. Add it all up, 2,167.5 milliamps. Divide that by an hour and you get that result, and this is the formula that you can use to calculate that. Now, what about expected battery life? For having determined milliampere hour, our example battery has got a capacity of 2,600 milliampere hours, and to calculate time you divide its capacity by the current demand of the average current demand, and that gives you a result in hours. In this case 4,318 hours or 180 days. So my typical server example of waking up, the little process of waking up, sending data and then going back to sleep, that battery would last for 180 days. Notice how the units are cancelled out. The battery capacity is in milliampere hour, the average circuit demand is in milliamps, the milliamp units are cancelled out, leaving just hours, so the answer is 4,318 hours or 180 days or 0.49 years depending on how you calculate it. So I've given some examples here. It's an example one is the circuit is consuming 100 milliamps for 10 seconds and then 1 microamp for the rest of the hour. Put those results in here, so it's 10 seconds on, 100 milliamps during the on time, and then 3,590 seconds off, consuming 1 microamp. Because the units are milliseconds, I've divided milliseconds by 1,000 to get microamps. That's 1 microamp there. Its total power consumption is 2,000.278 milliampere hours. A much bigger example is the circuit takes 10 amps or 10,000 milliamps for 25 seconds and then 20 milliamps for the rest of the hour, consuming a total of 89.3 ampere hour, very high demand. Or much lower now, 1 milliamp for 3 minutes and then 10 milliamps for the rest of the hour. So I've deliberately turned the on-off demand round there just to illustrate the point. Doesn't matter which way you do this, your calculation, you will always get the right answer. An answer of 9.55 milliampere hours. Because this is the most dominant part of the calculation, logically you should expect the answer to be very close to this dominant, and indeed it is. The dominant part of the calculation, or the demand, is determining the final demand. A circuit that uses 74 milliamps, I keep using 74 milliamps because that's how much the ESP8266 uses when it's using its Wi-Fi transmitter. So it uses 74 milliamps for 4 seconds and then 0.05 milliamps or 50 microamps for the rest of the hour, and that gives you an answer of 0.132 milliampere hour. Or finally a circuit that continually uses 74 milliamps, and the answer is 74 milliampere hours. It's 74 milliamps per second, per hour, per day. It's continuously demanding that amount of current. Using that battery pack as our example, going through those 5 examples there, the first one is 389 days, the second one is 1.74 seconds because it's such a high demand, and so on all the way through. So if you, in example 5 is using the ESP8266 continuously at 74 milliamps, that battery would last you just over a day and a half, 35 hours. But if you put it into sleep mode, the other extreme in example 1, sending data, going back to sleep, it would last over a year. Now I'm ignoring the fact that the batteries do have a little bit of self-discharge, but for theoretical example purposes, these are the answers to the examples. Now in reality, the current consumption is much more complex, more repetitive. It takes 74 milliamps, goes to sleep for 5 minutes, takes 74 milliamps, goes to sleep for 5 minutes, and does that throughout the reference hour. To determine that, there's a slight modification to the formula, which is the number of cycles that occur in 1 hour. Multiply that by the time on, time off, current off, and then use the 3600 as the hour reference. So here's my example one again, and showing that if it switches on for 5 seconds and then goes to sleep for 5 minutes, this is how you do the calculation. So how many cycles are occurring per hour? Well, the length of each cycle is 5 seconds plus 5 minutes, which in seconds is 305. So to find out how many cycles occur per hour, that's 3600 divided by 305 equals 11.8 cycles per hour. So that's that first calculation there. The time on, for 5 seconds it demands 74 milliamps. For 300 seconds it demands 0.5 of a milliamp. Therefore the total power consumption is 1.7 milliampere hour. So that 2600 milliampere hour battery pack would last for 2600 divided by 1.7 is 64 days. And that is typically what you will always find. Duration is not that great. Okay, so now what I've done is move the timing of my example out to 20 minutes, and we should expect a much greater battery pack duration. Let's see what we get. So 5 seconds on, consuming 74 milliamp, and then 20 minutes off, consuming 0.5 of a milliamp. Total, put the colors denote where the cycle is in terms of the calculation. I think that's fairly self-evident. Again, number of cycles per hour. Well, what's the duration of one cycle? It's 20 times 60 off time plus 5 on time is 1205 seconds. So you'll get approximately 3 or 2.987 cycles per hour. Put all those numbers into the equation and the result is 0.803 milliampere hour, and that battery pack would last for 135 days. Previously it would only last 64 days. So just note that the time has been extended, the time between updates is 4 times longer, but it didn't make the duration on battery power 4 times longer, it only doubled it. The square law going on. So although the time between updates was 4 times longer, it only doubled the effective battery life, or time on battery. So repetitive cycle process is almost identical. The only thing that is different is to determine the number of cycles per hour. So that's time on plus time off is the cycle time. So that pulse on of current and then the sleep current before it repeats again is 1 cycle, and add that to the calculation. Here's some slightly more complex examples, and I've shown how you would calculate that. So again, we're finding how many cycles there are per hour. This is 1 hour along here. Finding the area of one cycle, and the area of a triangle is half the height, half the base times the height. So it's half of a square. That's what I've done in the calculation. There are 4 cycles per hour in my example there. It's 15 minutes times 60 seconds times the maximum current, which is 50 divided by 2, that's 25 milliamps. How much time does it spend off? Well, it never goes off. It's always demanding current, so you can just make those zeros. And the milliampere hour demand of that circuit is 25 milliamps. If you filled in the gaps here with that part of the triangle, you would get a constant line at 25 milliamps to visualize that. Here's a more stepped example of current consumption. Again, we're trying to find out for one cycle, there are 2 cycles per hour. What is the area for one cycle, and what's the average? Well, there are 2 cycles per hour. For 2.5 minutes it takes 1 amp and then for 2.5 minutes it takes half an amp, and then for the rest of the time, for 25 minutes times 60 seconds, it takes 50 milliamps, so the total power demand is 166 milliampere hour. So we could take those values and divide the battery consumption by our milliampere hour consumption. So 2600 in the top example, that would last for 104 hours, whereas the example at the bottom would last for 15.5 hours. Summary of the calculation: first of all, the battery capacities are always quoted in ampere hour or milliampere hour. You have to calculate the average current consumption, and you do that by determining the number of cycles per hour, the time on current, the time on duration, the time off current, and the time off duration. Multiply that by the number of cycles and divide by 3600. In formulas, if there is no operator between formulas, it's a multiplication, and there in sort of prose in English, it's calculate the time in seconds for each cycle, record the current consumed for the on and off times for each cycle, determine how many cycles occur per hour, then multiply the number of cycles per hour by the total current consumed during one cycle, and divide the result by 3600 1 hour, and the result is the demand in milliampere hours. So find the average current consumption, that is the answer in milliamps. That's how much the circuit demands on average in milliamps, and then convert it into milliampere hours by dividing by 3600 if you're measuring in units of seconds. If you were measuring units of hours, you wouldn't divide by 3600, you divide by 1. So you could, if you measured and found an average of 1 amp over an hour, its consumption is 1 ampere hour. Divide that by 1. That's it, folks. That was a quick run through calculation of milliampere hours.